Hi, welcome to another edition of Calculus 2. We are going to start our conversation about geometry in three space coordinates. So this is the beginning of preparation for Calculus 3. We are going to go ahead and move from 2 dimension to 3 dimensions. Let's go ahead and do this short and sweet topic. So everything you have done since the beginning of your mathematical preparation in elementary school was in a two-dimensional setting. So you had the x and y coordinates there. Now we are preparing ourselves for a three-dimensional world. So we are going to have x, y, and z coordinates. So this is a three-dimensional coordinate system. Sometimes we simply refer to it as R3, and our familiar setting will be R2. Okay, best way to visualize this coordinate system is to think about the corner of your room or something. So you see here we have three coordinate planes. Let's color them so that we see what we are referring to. So this one is referred to as XY coordinate plane. So this is XY plane, and then we have, of course, YZ plane, and finally we have the XZ plane on this side. We are going to go ahead and make ourselves familiar with some basic facts about the three-dimensional coordinate system. More than likely, all engineering students are going to have a course in engineering graphics, and then you have much more detail to deal with respect to graphing in three dimension. Graphing in two dimension was already a rather challenging topic. You can imagine in 3D we need substantial amount of preparation. Okay, now first thing to do is to become familiar with what is x, y, and z anyway. So let's go ahead and see what happened in 2D. If I have a point here, the x coordinate is distance from the y-axis, and the y coordinate is the distance from the x-axis. Let's go ahead and color these things so that we see it clearly. And x is this one. So if we make a rectangle at the point xy, two sides of this rectangle are dimension x, the other two are dimension y. Well, how is that going to go in the xyz coordinate plane? If I consider a point here, then its distance from the YZ plane will be the x coordinate. So if I go from this point back to the green wall, that's going to be my x. If I come to the yellow floor or wall, what would that distance be? So coming from here down to the XY plane, that's going to be RZ. If I go to the blue one, what would be that distance? So this, well, that's parallel to the y-axis, and that's going to be a y coordinate. We can go ahead and make a box. Here we had a rectangle. Here we can make a box, and in this box also you can go ahead and label various coordinates. So this is z, this is z, this is z, and this is z, and y is these sides are y. Now it's getting rather crowded now, so x is this one and this one and this one. So we have 12 edges, and 4 of them x's, 4 of them y's, 4 of them z's. Let's go ahead and make sure we understand what happened there. It's very crucial that we understand what is x, y, z actually. So here's a little demo. We have a point. Here's our point, and I have the x, y, z coordinate plane. And suppose I want to show you the x coordinate. What's the x coordinate for me? Here, this is what's controlling the x of this box. Okay, you notice if I want to go negative, I go to the other side. My box is extending, that x of that corner is changing. So x of this point, you can see shown by these red edges. These red edges, they're all equal to x. Of course, our y is that purple line. The purple line, you notice I'm extending it, and if I want to go negative, it would be on the other side. I'm going back. And of course, the z is going to be our burnt orange color. This is the z-axis. So very crucial that we become comfortable with what is x, y, and z, be able to graph points in 3 dimension. So let's go back here. Suppose I ask you just plot a point, plot 2, 3, and say 4. So what does that mean? So we do the best we can with setting up our coordinate system. It is something like this: x, y, z. Now again, when you go to your engineering graphics, there's going to be a substantial amount of discussion as to how to set this thing up. After all, the issue is that you are trying to portray a 3-dimensional event in a 2-dimensional medium, and that's not a trivial task. We're not going to get into too much detail right now and postpone it to your next class. But right now, let's go ahead and see what do we do with 2, 3, 4. So we need a unit in these 3 directions. So let's just consider these things as a unit for ourselves. So 2 units will be 2 of this. So by now I have come to location 2. Now let's go after 3. So I need to go 3 of these units. So I draw my line parallel to the axis. Typical mistake is to go perpendicular to the coordinate you are on. We now try to maintain the perspective view, and so this is 1, say this is 2, and this is 3. So y coordinates become 3. Now let's go after z coordinate. Z coordinate, we go parallel to the z-axis, so perhaps this is 1, and then 2, and then 3, and say 4. So this is going to be 4, and the point I've arrived at is 2, 3, 4. Of course, you could have taken traveled through y direction first, then x, then z, or any kind of combination. So there are 6 ways of arriving at this location. You practice it. When you draw all of them, you are going to see a box. So you're going to see something look like this at the end. If you consider all possibilities. For arriving at this location, you have many choices, and they all bring you to the same location. Okay. Now, in 2 dimension, it was easy for us to get the formula for this hypotenuse. That hypotenuse was simply x squared plus y squared square root. What is it going to be in 3 dimension? Well, if you guess that the inner diagonal of this box, what is the length of it? Well, it's going to be square root of x squared plus y squared plus z squared. So that's the extension of the Pythagorean theorem in 3 dimension. Let's go ahead quickly show this thing. For example, suppose I want to measure this inner diagonal. We are claiming that that inner diagonal is going to be 2 squared plus 3 squared plus 4 squared. How do we show that quickly? Well, first go ahead, get the diagonal of this rectangle here. Again, this is in perspective, this is supposed to be a rectangle, and to get that, well, you apply the standard Pythagorean theorem, 2 squared plus 3 squared. Well, now go ahead and concentrate on this right triangle. Do you actually see that this is a right triangle? Again, this is an issue of perspective. You want to be comfortable with the fact that this is a 90 degree here. Well, what do? You get two legs, square them to get the hypotenuse. Well, this lower leg is this quantity, 2 squared plus 3 squared in square root. We are supposed to square that, and the other leg is 4, and we are supposed to square that, and then take a square of the whole thing. Well, of course, when you square root and then square, you just get 2 squared plus 3 squared, and then you add the 4 squared to it, so you get the formula in this case. So what we have is a Pythagorean formula in 3 dimension, and let's apply it to distance. So make a distance formula in 3D. Distance formula in 3D. So that is going to be, suppose I have a point P1, which is x1, y1, z1, and I have point P2 that is x2, y2, z2, and so the distance of these two, just like ordinary algebra classes, this is just you have to take the differences. Now you have 3 of them, and take each difference, square it, add them up, and take square root. That's going to be our distance formula. Another formula from college algebra is the so-called midpoint formula. Let's go ahead, extend that too. If you remember, midpoint of P1, P2, the one that you you are familiar with, just has 2 coordinates, and it would be easy for you to show that when you want to go to 3 coordinates. There's a additional one of these. So here is our midpoint formula. Another basic formula from the high school classes is this equation of a circle. So you remember, equation of a circle was, well, suppose your center is AB and your radius is R. So you want to find out the equation of a circle. So, well, let's consider this point xy and write the distance formula. So x minus a squared plus y minus b squared. Well, let's square it to clean it up. So it has to be r squared. Well, in 3D, our shape is going to be a sphere. And suppose the center of the sphere is, let's call it ABC, and the radius of it, let's just continue to call it R. The equation is going to be x minus a squared plus y minus b squared plus z minus c squared, and all of that is equal to r squared. So what is this formula? That is really the distance formula squared on both sides, and that gives us our spheres. We had talked about standard unit vectors before. Standard unit vectors in 2 dimension, we had called these things I and J. So these were the 2 vectors. This was, in that setting, this was 1 0, and this was 0 1. It was in 2D. So that was the definition in 2D. In 3D, well, we have 3 of these, and typically they are drawn in this position, that this is your I, and this is your J, and this one is going to be your K. designation of these things. I will be now 1 0 0, J is going to be 0 1 0, and K is going to be 0 0 1. Well, you can notice that we are going to run out of letters in that style. So when you go to your linear algebra class, they might call this one E1, this one they might call it E2, this one might they call E3, or similar kind of a terminology, in order to get ready for R4, R5, and so on, in which case IJK is not going to be a good notation. Addition, subtraction, calculation of length, unit vectors, vector addition, scalar multiplication, these are all exactly same way that we did it for 2-dimension. So exact same approaches, and definitions are applying. So if I have a vector V that is with components A, B, C, now the norm of V, we said you're supposed to draw double vertical, but we were avoiding that. Norm of V is simply sum of squares of all three components. So we are applying Pythagorean in 3-dimension. Unit vector in direction of V, let's just practice that one. If you have a vector of some arbitrary length and you want to cut it down to size, so it's of length 1, you just divide it by the length of it. So let's just remind ourselves, pretty soon we are going to make our formulas a little bit cleaner by drawing fewer lines. So that is all the same as before. Some issue that comes up in some of your homework is the issue of what is parallel vectors. Exactly what you think. If you have a vector and you multiply it by some number, it might stretch or shrink. So if you have a vector V and double it, well, these two obviously are parallel, they have same direction. Except notice that if you also multiply by negative number, as far as our text is concerned, these are all considered to be parallel vectors, minus 2V. So these two are in the same direction, and these two are in opposite direction, but all of them are considered to be parallel to each other. These are all parallel vectors. One of the issues that are that's rather hard to see in 3D, but was easy to do in 2D, rather easy at least to see, if you have 3 points, the issue comes up: do they line up, or is it like they are offline? So if they line up, we have a terminology for this thing. We call these type of setting as collinear. So collinear refers to a set of points that happen to sit on a line. Now, collinear points are rather easy to see, at least visually easy to see in 2-dimension. Does a line pass through them or not? Other than visual, how would you actually check it? Well, you consider 2 points and you consider 2 other points. If the slopes are the same, so if slope is same as the other slope, they line up. If the slopes are different, of course, they don't line up. So here, if you have this situation versus that one, this is some slope, this is some other slope, M1 is different from M2, so this is not collinear. You can apply the same idea in 3 dimensions. So if I have point P and Q and R, in 3 dimensions it's very hard to see if they are collinear or not. So I can consider a vector PQ, let's consider this thing U, and then PR, let's consider this V. The 3 points are going to be collinear if one of these vectors is some multiple of the other vector. Like if one of them is double of the other one, three times the other one, or minus 5 times the other one. If it so happens that one vector is a multiple of the other one, then you know that these are parallel, and therefore they all going to line up Another basic issue with respect to notation is, well, how are we going to write our vectors? Suppose I have the vector 2, 3, 4. Okay, 2 in the x direction, 3 in the y direction, 4 in the z direction. Are there other ways of referring to this thing? Well, I can write this thing as 2i plus 3j plus 4k. Remember, these are our standard unit vectors. What does that mean? Is 2 of 1, 0, 0, 3 of 0, 1, 0, and plus 4 of 0, 0, 1. So one of the great services you can do to yourself is to get familiar with the terminology and the notation, because we are going to be building on these things. The problems in this section are very straightforward. You want to practice as many of these things as you can. Just go to the end of the section in the textbook and aim for doing 20 or 30 of these things in a matter of 15 minutes. Essentially, that's how long it should take for you to be sure that you have the basics covered. You notice that we don't have any advanced formulas or anything of that sort. The beginning of this topic is very simple, but it quickly accelerates, and we are going to get into a rather steep ramp later on. So you want to get the basics done. Okay, so this was a short lecture. I'll see you next time with the more advanced topic. We are going to talk about planes and lines in 3 dimension. Until then, good luck and God bless.